Here's a number that should make you pause. By the end of this decade, by 2030, running artificial intelligence globally could require as much electricity as an entire nation consumes. Not a small nation. We're talking power demands on the scale of Japan. Or Germany. Possibly more. And right now, the grid isn't ready. The infrastructure isn't ready. The planet, frankly, isn't ready. Data centers already consume somewhere between 1 and 2% of global electricity. That number sounds small until you realize it's been doubling roughly every few years. And the models are getting bigger. The queries are getting more complex. Every time you ask an AI to generate something, somewhere a server rack pulls enough power to run a hairdryer for several minutes. Multiply that by hundreds of millions of users. Every day. Every hour. This is what engineers call the power wall. And unlike most walls in tech, you can't code your way through it. So here's the question nobody in Silicon Valley wants to answer out loud. What happens when intelligence scales faster than the grid can follow? What happens when the smartest machines ever built run headfirst into the dumbest possible limitation? Not enough watts? You get a crisis. And crises, historically, are where the most interesting ideas emerge. Enter a startup called Esnor, and a chip architecture that its founders claimed could run certain AI workloads not 10% more efficiently. Not twice as efficiently. Thousands of times more efficiently than the GPUs powering today's AI revolution. That claim sounds insane. It probably should. But the physics behind it is real. And understanding it requires going back to something your high school teacher glossed over. The actual cost of thinking. Every computation costs energy. Every single one. This isn't a design flaw. It isn't an engineering oversight from the 1950s that nobody got around to fixing. It is thermodynamics. It is the universe's way of charging admission for the act of knowing something. For decades, the industry had a beautiful trick for hiding this cost. Transistors got smaller. Every generation of chips squeezed more operations into less space, consuming less power per calculation. This was Moore's law in its full glory, the miracle that gave us smartphones, laptops, the modern internet. More intelligence per watt, year after year. That miracle is ending. The transistors are now so small they're measured in atoms. The laws of quantum mechanics start misbehaving at that scale. The efficiency gains are flattening. And AI, of all things, arrived at the worst possible moment, demanding exponentially more computation just as the industry's best trick for making computation cheaper is running out of road. Here's where it gets philosophically interesting and slightly absurd. The chips running today's AI were not designed for AI. They were designed for certainty. A conventional processor, a GPU, a CPU, any digital chip you've ever touched, operates on a beautifully simple principle. A transistor is either on or off, 1 or 0, yes or no. It never wavers. It never second-guesses itself. It is the most decisive thing in the universe. That reliability is perfect for a spreadsheet. It's perfect for a banking system, an operating system, a video game rendering engine. Tasks where the right answer is a fixed, repeatable fact. But here's the uncomfortable truth about modern AI. It doesn't work that way. AI doesn't deal in certainties. It deals in probabilities. When a language model generates the next word in a sentence, it isn't looking up the correct answer in a table. It's sampling from a probability distribution, essentially rolling a weighted die across hundreds of thousands of possible outcomes thousands of times per second. To do that on deterministic hardware built for certainty, you have to fake the randomness. You force a machine that speaks in absolutes to pretend it understands nuance. And that performance costs an extraordinary amount of energy. You're not just computing. You're computing the long way around. Now here's the twist. And it's the kind of twist that, once you see it, makes you feel slightly foolish for not seeing it sooner. Inside every electronic circuit, there is noise. Thermal noise. The random, chaotic flickering of electrons driven by heat. Engineers have spent 70 years treating this as the enemy. They raise voltages. They build error correction systems. They design entire architectures around the goal of eliminating this randomness. Keeping signals clean, keeping transistors decisive. What if that was the wrong instinct all along? What if the randomness isn't the bug? What if, for a specific class of problems, probabilistic problems, AI problems, the randomness is exactly the feature you need? That's the intellectual leap at the heart of what Esnor is building. And it starts with a concept they call the p-bit, the probabilistic bit. Forget the transistor flipping cleanly between 1 and 0. A bit doesn't flip cleanly, it fluctuates. It exists in a state of natural uncertainty, leaning toward one outcome or another based on how you configure it, but never locked in. You don't command it, you bias it. You nudge the probability. And here's the energy implication. In a conventional chip, you burn energy to suppress noise and force a clean signal. In a p-bit system, you lower the voltage intentionally. You let the noise appear. You use it. The randomness that engineers spent decades trying to eliminate becomes the computational resource itself. Instead of simulating probability at enormous cost, the hardware provides it for free. The randomness was always there. You were just paying a fortune to silence it. This is not magic. This is thermodynamics running in the opposite direction. When you connect many p-bits together into a network, something remarkable happens. The system stops behaving like a program and starts behaving like a physical process. It drifts. It settles. It finds stable configurations the way water finds the lowest point in a landscape, not through step-by-step instructions, but through the natural dynamics of the system itself. In conventional computing, you enumerate possibilities. You calculate, you compare, you select. In a probabilistic system, the hardware does something closer to intuition. It samples the answer from the structure of its own behavior. Computation becomes less about executing logic and more about physics arriving at equilibrium. Esnor calls this architecture a thermodynamic sampling unit. It doesn't run programs in the traditional sense. It samples probability distributions directly from physical behavior at speeds and efficiencies that conventional hardware cannot touch for these specific tasks. Their upcoming chip aims to scale this to hundreds of thousands of probabilistic elements on standard silicon. No exotic materials, no extreme cooling systems. Just a fundamentally different philosophy about what computation is and how physics can do the heavy lifting. At this point, a reasonable person asks the obvious question. If this is so elegant, why hasn't it been done before? Because elegant physics and practical engineering are different conversations. Analog systems, systems that operate in gradients rather than clean digital, states are extraordinarily sensitive. Temperature fluctuations change behavior. Manufacturing variation across chips introduces inconsistency. Components age and their behavior drifts over time. In a digital system, a transistor is either on or off and small variations don't matter. In an analog probabilistic system, small variations are the whole game. Managing that sensitivity at scale is not a solved problem. It's a frontier. The engineering required to make hundreds of thousands of p-bits behave reliably enough to be useful, not so rigidly that you destroy the probabilistic advantage, is genuinely hard. Calling it hard is probably generous. It is one of the more technically demanding challenges in semiconductor design today. And then there's software. Here's the villain in this story. Not a company. Not a CEO. The villain is inertia. The entire modern AI software stack, PyTorch, TensorFlow, CUDA, every framework that every AI researcher on the planet uses every day assumes deterministic computation. It assumes matrix multiplication on conventional hardware. It assumes the rules of digital arithmetic. A thermodynamic chip doesn't play by those rules. You cannot take a model trained on a GPU and drop it onto a probabilistic processor the way you copy a file from one folder to another. The model has to be rethought. The training process has to be redesigned. The entire software ecosystem has to be rebuilt around a different computational paradigm. That takes years. It takes developer adoption. It takes companies being willing to invest in something that doesn't immediately plug into their existing infrastructure. And historically, that's exactly where promising hardware goes to die. Not because the physics failed. Because the ecosystem never materialized. This is the real race Nora is running. Not against other chip companies. Against the gravitational pull of the status quo. Here's the practical reality for you as someone who uses AI tools, who pays for AI subscriptions, who reads headlines about AI data centers consuming the power of small countries. The energy crisis in computing is your problem too. When the cost of running AI goes up, prices go up. When data centers compete with cities for grid capacity, infrastructure degrades. When the environmental cost of AI becomes impossible to ignore, regulatory pressure follows, and the tools you rely on become more restricted, more expensive, or simply slower to improve. What Esnor is proposing isn't just a clever chip design. It's a different philosophy of computing, one that works with the nature of reality rather than fighting it. And if that philosophy can be made practical, it doesn't just make AI cheaper. It potentially removes the single biggest constraint on how intelligent our machines can become. The power wall is real. The question is whether the industry finds the door before it hits the ceiling. Here's the lesson, stated plainly. For 70 years, computing was built on the assumption that noise is the enemy. Certainty is the goal, and physics is an obstacle to be engineered around. That assumption worked brilliantly. It gave us everything, and now it's becoming the thing holding us back. The most interesting ideas in technology right now are the ones that stop fighting physics and start using it. The ones that look at the thing everyone called a flaw and ask whether it was actually a resource all along. Probabilistic problems, and AI is fundamentally a probabilistic problem, may deserve probabilistic machines. That insight sounds simple. It took 70 years to take seriously. The next time someone tells you AI will keep scaling forever, ask them where the electricity is coming from. And the next time someone tells you the current approach to chips is the only approach, remember that the most expensive thing in modern computing might be the noise engineers spent decades learning to silence. Sometimes the answer was there the whole time. You were just paying to drown it out. If this kind of thinking interests you, the physics behind technology, the hidden constraints shaping the future, the ideas that sound radical until they become obvious, subscribe to this channel. And if you think someone else needs to hear this, share it. The conversation about AI and energy is only getting louder. You might as well understand what's actually being said.